So let's look into our example 2. So in example 2 here, the experiment we have is to draw a card out of a standard deck of cards. So in case anyone is still not familiar with what a deck of cards is, a standard deck of cards is, then we can quickly look over my screen here. But a standard deck of cards is basically this. We got all of these are 52 different cards. Each one of these is a suit. We got the hearts here, we got the diamonds here, we got the clubs here, and we got the spades here. And these cards with a picture on that, they are referred to as the faced card. So our first question would be, if we draw a card out of that, then how many outcomes are there in the sample space? Or in other words, how big is the sample space we're working with? So let's make that SS a little bigger. So you can quickly go back to the screen here and count, but truly there are 4 major suits, 13 in each suit right there. So here we're looking at the answer being 52. Nice and simple. In our next question, we're starting to look for the actual probability. So we'll be asking, find the probability of getting a black king. So finding the probability of getting a black king. So you can see that find the probability, or previously in example 1, what is the probability of getting all that standard phrase they're asking for a probability now can be represented by a symbolic statement. We're getting ready for that. And then the event we recognize here, getting a black king. And so of course getting a black king, but what's mainly being asked for is the black king right here. And so that's our event. So now I'm going to be putting that inside of my parentheses here. I want to be getting a black king. And so of course finding the answer to this question is still very simple. But I'm not mainly aiming at getting the answer of the question here. What I aim here is to clearly understand the event being involved here. And so if we are looking further into the event itself, so mainly we're looking for black king. So now as we realize, it's just the language. A lot of time it doesn't indicate clearly, but black king, really the way how we're saying it, the way how we write it down, but behind the scene there has been 2 requirements being involved in here. Being black as one property, being a king card as another property. Because you can see, now quickly look back into the card, you can see that being black are all of these cards here in the 2 bottom rows. Those are the black cards, and at the same time looking for a king. Among these face cards, we have these cards here, what we call the kings. And so really, or logically, there has always been, and it's like I said again, it's just the language that we're using, and a lot of time in any language we never have to be that precise, but being black, being king here, really there was an and keyword. There's an and logical keyword that connects them. We want black as one property, and at the same time we want having a king. And so now and this is the very symbolic statement. Even we came up with the symbolic, but here it's even more to tear down into just all that bare bones structure over here, and every truth behind the scenes about the event has been brought up here. So we're looking for black, and at the same time we're looking for king card right here. So I have to point out one more thing, that see the keyword and right here, we're looking for those outcomes. The intention here is we're looking for those outcomes that meets the two requirements at the same time, simultaneously. Failing one of the requirements here, it's not going to meet, it's not going to pass. So think about, say, if any of you are taking classes at any college, then think about one day you come and you discuss with your advisor and say, hey, Mr. Whoever, I need to graduate out of this college here, what am I supposed to do? And your advisor advising you that in order to graduate, you need to successfully pass math and English. So when he's saying math and English, he means you have to pass both of them. You need to meet both requirements. Failing one is not going to get you through the door. And so, same way here, we're looking for the probability of getting black king. The language is only saying black king. We didn't see the and here, but really, like I already explained, there was an and logical keyword here that connects the two requirements here. But so now as we see that and, it means we have to only look for those outcomes that meet two requirements. Otherwise, those outcomes are not going to get counted. And so I'm only using counting for now. And so let's have a look into our screen here. I want black. So all of these, as I already circled previously in the black circle here, those are black cards. And then at the same time, I'm looking for king card. So king is here. But then the only two cards that meet both requirements are these two guys right here. So there's this king, this club king, and there's this spade king right here. And so after seeing through the cards and mixed circle, and there's this area, usually I call it, it's the overlap of two, requirements or two events right here. Then we count those outcomes. And so now in counting, we found the answer to that. We found two cards out of the whole sample space being 52 cards. And so now we are looking at reducing the fraction 1 out of 26. And that's how we found the answer. And once again, the same fundamental being used here. We're looking at the number of outcomes that meet our event and divided by over the number of outcomes, the total number of outcomes in the sample space. And so let's even look further before we close down this question and move on to the next one. But this kind of event we're looking at being black, one requirement, and at the same time looking for a king. So we found out that this event actually involved two other little requirements inside of it. And so this event, this kind of event here is referred to as a compound event. It's a one compound event where each of these, being king and being black, two little requirements, then we refer to them now as being black is only one single requirement, being king is another one single requirement. So each one of these, being black and being king, inside of the compound event now, we refer to them as a simple event. I myself might use the term single event sometimes as well. Simple event or single event. You might hear me saying single event sometimes. Or I even call the terms sub-event, as indicating that each one of these is a sort of like a sub-level compared to the bigger compound event level. And so now let's categorize those kind of compound events that we're looking at here. But so right there in our question B of example 2, right there, then, well, let's say I'm going to look at two capital letters here to symbolically represent two simple events, any two simple events, or two single events. Then in our question B of example 2 that we just did, then the event, the compound event we looked at was, I would call it form 1 right here, but namely it was symbolically A and B. So that was the kind of compound event connecting two simple events, any two simple events by the AND logical keyword. And so here's the thing. How did we answer that question? Find the probability of having A and B. So I have to give this as advice, but the only way for now, the only way to find this answer is to count. Find the count and put that over the number, the total number, in the sample space. And that's the only way. Another advice here before we move on too far is that you might have heard somewhere outside of this class statistics that probability of A and B can be found by finding an individual probability for A and another separate individual probability for B and multiply these two. Now, I'm telling you, this is not correct right here. What you might have heard is for a different kind of settings right here, but we will almost never have to use this as a formula to calculate probability of A and B. We will always just, anytime it comes to the compound events A and B, all we do is find the count and put that over the total in the sample space. And that's how we handle this kind of compound event right here. So question C, just like that, I'm going to bring up another similar question using the same kind of compound event. So let's say we want to find the probability of, well, I would call getting an odd spade. Okay, and so once again, setting up the symbolic statements, P in parentheses, and our events, and at this point you have seen oftenly enough, so the event is easily, the big events is always right after that famous phrase, the famous word phrase, what's the probability of, or find the probability of. So here's our event. But now if you're looking at this here, our real target is looking for odd and looking for spades. So you see written language, or a lot of time in short, the spoken language, we just say odd spades. But now, indeed, what truly happened now, and allow me to also even skip that term getting. All we need is now, we're looking for odd. It's one property in our event, in our main events. But then the other requirements here is we're looking for being the card being a spade. And so, as a matter of fact, what connects the two requirements here is, once again, the way how the language runs makes us understand that it should be the AND keyword, right? The AND logical keyword. And so now, once again, and we have seen some generalization of how to get this problem done. So remind yourself again, the only way of doing this probability on this kind of compound event here is to look for the count that, those outcomes that meet the two requirements here simultaneously, or to meet the two requirements together. So failing one is not going to make it counted. So here, being an odd, and by the way, odd is a property that only exists among the numeric cards. So there's no reason to look among these guys with a picture, because they are not numbers, and it's the way how a standard deck of cards is. Some cards are not numbers. And so, and by the way, since we're now starting to talk about properties on numeric cards here, now I've taught different places and some area of the country. There are some regions of the world, people regarding to the aces here. I don't know why my picture here, they using that as a T. I searched for this picture over the internet, but these are the aces. So some area of the world treating aces as a non-numeric cards, meaning they're just some other kind of picture out there. And of course, people call these the face cards because these pictures are really some kind of face. So that's just terminology. So these are the face card. There are 12 face card here, but some area, like I said again, some area of the world call these aces here a regard to these aces here, and that's what I meant as non-numeric cards. But also there were regions, part of there were some small groups of people considering these as numeric. So it all depends. So how about in this problem, let's in my example here, and be aware that anytime you're doing any card game for probability questions, then there has to be a note somewhere in each of your problems to indicate how to concern about what to regard aces as. So some problem will regard aces as a numeric. Some other problem you might have run into regard aces as numeric. So how about right here in this example, let's consider aces here as numeric. It's just me. But so now back to the question here. I'm looking for odd here, and odd is a property that exists among the numeric. So that means we got, this is the odd, that's another odd, we got those odds, we got another one here, and so you can really count a lot faster than how I do that. So these with the light purple stripe through, I'm trying to represent these are all the odds that we can count here in our cards. And this entire line right here, where I cross through with a light reddish line right here, are all the spades right here. And so those outcomes we're looking for, once again, odd and spades. We refer to those that where the light purple meets with the light red right here. So it makes sense that this ace here, once we consider ace as a numeric here, then ace is a 1, being considered as 1. And so this is an odd number and also being a spade. So on this thing here we cannot count because it fails one requirement. Only these guys where these outcomes where the light purple and the light pink meet together, that's indicating we have those outcomes meet two requirements simultaneously. So we now have 1, 2, 3, 4, and 5 outcomes that really meets the requirements, the two requirements. So now we have 5 out of 52. And that is our answer. Okay, so question D now of the same example. A different question is being brought up here. Let's say find the probability of, we want to be getting a red or an even number. Alright, so simple enough that you can see we have that same starting out phrase here, find the probability of getting. So I'm going to set up my symbolic statements here, E in empty parentheses. The events recognized, once again, simple to recognize it, that it's getting a red or an even number. So basically it means a red card or an even number. So that's our event being underlined in red ink. So now when we put that in symbolic statement right here, then red, you can recognize immediately that red is one, being red is one property, one requirement. we have another requirement here being involved, that being even. So two different properties, and red is about the color, but even is a property that exists among the numbers. So, and the keyword we recognized this time, there was that, and it's, now it doesn't matter if we use the spoken, the written language, or even the symbolic language, it's all the same. We have to put the keyword or here. That's quite easy to recognize. And so now, so when it gets to the kind of statements where it has two events, two separate requirements here, I shouldn't say events too rushly, but two separate requirements, and they are being logically connected by the or. Let's try to understand that a little bit. So first of all, think about the two requirements, and then or here. Now, a lot of time, the or here is being understood as the either or. Either this or the other one. Now, be careful with that way of thinking, because there's actually a lot going on in this or here. When we say either or, it might be dangerously thought that only one of these get counted or can pass. But here's the actual interpretation of the or here that we're doing in probability. I normally teach my students to understand this or here as the term, think of that as long as one requirement is met. As long as one requirement is met, we're going to count that outcome. So I put up that scenario again about meeting with your academic advisor. One day you go to Mr. whoever asking for academic advice and asking him the question, Mr. whoever, if I would like to graduate out of this college right here, what am I supposed to do? And this time he's answering you that in order to get out of the college, you have to pass math or you pass science. Pass math or passing science. So when he say or here, really he means as long as you pass one requirement, passing math or passing science is good enough for you to get out and graduate out of the college. And so, even though not being explained when we are speaking, but see the way how your advisor advise you means as long as you pass one requirement, one of your requirement is met, you're good to go. And so here the same way that we carry that same exact logic into doing the or compound event here. And so when I'm looking for red or even, so meaning now as I search through my cards, then the way we count now is that as long as you see a red, we put it in our count. Or as long as we see an even, we put it in our count. Or more specifically, as long as you meet any of these events being a red or an even number, you put it in our count. And so that also means there could be those outcomes to be aware ahead, but there could be those outcomes that meet both requirements. That works too, because like I said, as long as one requirement is met. All right, so let's now turn over our attention over to the cards on the screen here, and let's find out. So as long as one requirement is met, here we're looking for the red, so all these red count, don't they? We count all of these guys. So any of those guys count, and there are already 26 of them. We count them all, because as long as one of the requirements is met, here we're looking for red as one requirement, or even as the other requirement. And then being even, or those numbers, so I'm going to switch color, but these are the number over here. So that's even. So now I put up all the evens right here. But remember, the idea is as long as we found one of the requirements. So these evens, including these guys outside of the light purple, is also count too. So we're going to count everywhere that the light purple line hits, including some of the face cards here, and anywhere that the light pink cross through. So these are all the entries that we count. So let's now really count. So we've had all these 26 cards that has the purple light crossing through. And additionally, and I just use that term additionally, we've had all those 2, 4, 6, 8, and 10 more additional one add up on top of that. So our count here totally came out being, that was 26 plus 10, so 36 altogether out of 52, which in turn reduces down to 9 over 13. And so I approached the problem here completely through the count, and very shortly I'm going to show you an alternative for the exact same problem, for the exact same question, but we're going to approach it slightly differently. But here, keep it in mind that we have this way of thinking, this way of logical thinking right here. The OR here means as long as you found one of the requirements, we're good to go and put that the outcome in our count. Okay, so the exact same question, and no need to go anywhere further in that, but allow me to explain in a completely different approach here. So the earlier approach, how I got the answer, got to the correct answer, but completely through the counting, based on counting, and that worked when you have the entire sample space displayed in front of you, like this case right here. So going through counting is perfectly fine. But in case you're going to be working with bigger problem where the sample space is no longer presented in front of you anymore, then counting is going to be really challenging. So in that way, allow me to come up to explain a different approach here for the exact same kind of problem. What we're looking here is the type of event, even though I didn't formalize it yet, I didn't categorize it yet, but the kind of event we have here is it's having two requirements connected by the OR keyword, the OR logical keyword. So for this other approach I'm about to show, we're still going to rely on the exact same, it's all still starting out from the same understanding that the OR here means, one more time, and allow me to write it in a different place here, as long as one of the requirements here is met. And those requirements are good to go in your count, in your consideration. Well, I keep saying count, but here we're going to be counting differently with a little more math involved here. So if we look at this term, this way of saying as long as one requirement is met, it actually means it has a one further impact here. It means we expand possibilities. We expand our count to include more possibilities. You can take a pause on the video and think of what I'm saying here. When you say, as long as, when you explain to somebody that, hey, as long as you meet one of the requirements here, or as long as you see an outcome that meets one of the requirements here, you actually, when you're explaining that, you actually, the person who is listening to what you're saying can understand that this means we're expanding our count to include more possibility. And so now, including more possibilities, the famous mathematical operation means we're going to be adding, because we're including more. We put more in, so we're adding more in. And so now, in the way how it is, then logically it makes perfect sense, and don't worry about formulas or anything like that. We actually trying to recognize the formulas on our own here. So what makes sense here is, why don't we just find separately the probability for red? Because like I said, as long as one requirement is met, so why not just start out look for red or look for even first? Look for one of them, and we include looking for the other guys, looking for the other events. And include means include more possibilities, because being red is one possibility, being even is another possibility. Add them, and that's what including more means. Okay, but here's the, when we just simply doing things like this, adding two separate probabilities, then, well, let's grow the math side by side with this. The probability of being red here, simply through the cards, we're looking at 26 red out of 52. And there's a reason why I don't reduce the fraction here, just to make it easier for the later step. The probability of the even numbers, we look straight through our counter here, and we have 20 out of 52. And we add them. But so now as we start doing this, then you have to be careful and make sure you keep it in the back of your mind sometimes, anytime. That's what I meant. Anytime you're doing, including more than each one of these separate things already have those outcomes that has the two properties simultaneously. So each one of the red here, in the red group, there's already some of those being even, and also in the even group, there's some of those being red. So in other words, what I'm saying is, within each one of these outcomes, there are always those outcomes that meet two requirements together. And so if we're just simply adding, then we're going to be doubling those outcomes that meet two events. So here we need to roll them out. So simply adding to be explaining about including more possibilities. So we're simply adding, but we need to make sure we subtract out, exclude out those that have two properties both met. So in other words, I'm taking out red and even. Otherwise, we're going to have duplicates. So once again, if it was unclear of my explanation, it's just what I'm saying now is simply just when you're adding up, just make sure you subtract out those guys, those outcomes that meet two requirements simultaneously. And so in our count here, we can see that red and even, or those, we have 10 of them. So looking at the picture here, actually these are the ones that, so my mouse movement here is indicating those red and evens ones right here, in that zone right there. And so 10 out of 52. And so the count here brings us to the final total again, being 36 out of 52. And of course now reducing the fraction. That gives us 9 out of 13. All right, so we can now put into our list of those generalized understanding about compound events. So earlier, let's summarize again. But earlier we looked at the compound event A and B, and to find the probability of that kind of compound event, the only way we're doing here. And for the rest of the course here, we're going to have to strictly get the count over the total in the sample space. But then for this kind of compound we just learned in question D, then A and B being two simple events again, then what we looked at was the A or B. And so to answer that question, find the probability of those that meets the requirement A or meets the requirement B. One way we can do is to put the count again, find the count over the total number in the sample space. But we get that count relying on the logical explanation that this OR here means as long as one requirement in my list here is met. Okay, so that's one way to approach. And in my alternative explanation of the same question we've seen earlier, then this exact same kind of problem can be used as a formula. Anytime we're looking at probability of A or B, we can use this formula here. We find a separate probability for A, and we add to the separate probability looking for B, But once again, be aware that each one of the separate events here already has some of those outcomes where it meets both events. So in that way, we need to, in our formula, subtract out the probability of running into those outcomes where it meets both events, or in other words, probability of getting A and B. And so this, eventually, a lot of time we're going to be working with the kind of data or the kind of problem where sample space is not directly presented to us. So eventually this, using the formula approach, became more popular. And so this formula over here, the name for that is the additional rule. And now in the last question of this current example, we want to find the probability of getting a heart, okay, that shape right there, or a faced card, meaning those cards with the face on it. Okay, so now having done this many times, we can easily put up for ourselves a P in parentheses, the symbolic representation of this question right here. The event, once again, be easy to recognize, looking for a heart or a face card. And that now, in our understanding just previously in question D right there, then we came to a compound event looking for, what we're looking for here is one requirement being a heart, or the other ones, the other requirements. So I should have used red ink here, or being a phased heart. And so I'm going quite extremely symbolic here, but you know, when we are engaged into that mode of working with this problem, you understand what I mean by heart or phased right there. So we have two approaches. So allow me to go through both approaches again. But I probably don't need to go as detailed explanation as in the earlier question indeed, because we're having similar, very similar situations. All you keep in mind here is this or here means as long as you found a heart or you found a face card, that counts. So as long as one requirement is met. And that's fundamentally what we rely to. Alright, then looking over to our screen here, the hearts are all here. This one line of one light red line right here is crossing through all the hearts. So these are all the outcomes that we count for now. We put them in our counts because as long as one requirement is met. So we found all the hearts right here, including all these face cards here. And additionally, we're also looking for these with the light purple line crossed through them. These are the face cards right here. And like I said, as long as we meet one requirement being the heart, or we meet any of those outcomes being a face card, we put them all in the count. And then once again, the picture is showing it clear that among the face cards or among the heart right here, there are some of those outcomes that meet both requirements. So be cautious, be aware about that, so that later on when we bring up the formula and use it, we're going to have a way to subtract it out successfully. But so here, relying on the count as long as we meet one requirement. So these are all the red. Here we got 13 red. There's one row here. And additionally, outside of that, we got all these guys. I mean, there's no reason to recount these guys. So outside of all the reds here, which already had some of the purple, but outside of that, additionally, we have 9 more hearts that we should put into our count because they meet the other requirements. And so now totally we are looking at 22 out of 52. And that fraction there reduces down to 11 out of 26. And once again, I just want to remind everybody again, we always relied on that the number of outcomes that meet our event. So our event here is a compound event that drives we to count differently. But now we get that count 22, but that's over the total in the sample space. And so that's how we approach the problem as counting, through counting, directly counting, in case the sample space has easily been presented right in front of you. But alternatively, we can also, the exact same problem, you can also approach that as, well, allow me to rewrite it as, we're going to find, so here's a different way how we can approach. So also you can find a separate probability for hearts, and then we can find a separate probability for being a faced card. Add them up, and then we make sure we subtract out those outcomes that meet both requirements. So here, heart and faced card. And so in that way, the number of hearts we're looking at is being 13 out of 52. The number of faced cards here specifically, we're looking at 12 out of 52. And then once again, having the picture here, one more time, let's have a look at the picture here. But these are the one having two requirements being met simultaneously. So we're going to subtract out 3 of them out of 52. And so in that case, our math turns out to be 22 out of 52. And once again, that reduces down to 11 over 26. The exact same answer as we have found in the other one. So 2 different approaches.